we've got a circuit as shown below here, and it's been connected for a long time. That means there's no current flowing through this branch anymore, right? Because the capacitor's filled. When they say for a long time, that means, hey, all the capacitors are filled with charge. And if you have a branch in your circuit that has a capacitor in it, if it's been on for a long time, that capacitor's full and there's no current flowing through that branch anymore. Okay, and it wants to know what's the voltage across this capacitor for part A. And then for part B, if the battery is disconnected, that is, if we get rid of this, if we got rid of this battery, how long before this capacitor has 1/10 of its initial voltage? Okay, so we're going to figure all that out. So here's what's given. It's all in the picture. Let's for part A, let's find the voltage across the capacitor. So we'll say V sub C, or delta V sub C, the voltage drop across the capacitor. Okay? Now, here's the main thing to realize in here, and it takes some getting used to. But since there is no current flowing through this branch right here, that means whatever current is flowing through the 1 ohm resistor is also flowing through the 4 ohm resistor. Does that make sense? Because there's no other, the current's not going to go here. So if I've got, let's say, 3 amps going through here, I have to have 3 amps going through there, which means what is true? These two resistors are actually in series. Okay, and of course by the same logic, the 8 ohm and the 2 ohm are in series because there's no current flowing through here. So all the current is the same. So what I'm going to do is figure out what the equivalent resistance of this is, and then figure out, well, we don't even need to go that far. What I am going to do is I'm going to redraw this circuit. So here's my 10, and I'm just going to ignore the capacitor for now. I'm going to look at this guy. Now these two are in series, so this is actually going to be a 5 ohm resistor, and this is going to be 8 plus 2 is 10 ohms, right? Okay, now I completely redrew it. That's okay. I like to redraw circuits a lot, and it takes up a lot of paper, but that's the way I like to do it. So what does that mean? Can I figure out what current there is through this branch now? Yes, because what is the voltage drop from here to here? Well, if this is 10 volts, this has to be a 10 volt drop. So if delta V equals IR for any resistor, okay, I can solve for I. So I is going to be equal to delta V, which is 10 volts, divided by the resistance, 5 ohms, and that gives me 2 amps. So I know that there's 2 amps flowing through here of current. And then by the same logic here, I've got I through here. Well, that's going to be 10 volts. We're going to lose 10 volts. We've got 10 ohms, so that's 1 amp. Oops, 1 amp. Okay, so I've got 1 amp flowing through here. Now let's go back to this circuit right here, and I'm going to redraw it again. Let's see, let's make space over here. So here's my 10 volt. But now I'm going to kind of redraw it like this, because it makes it a little bit easier for me to see what's going on. And you can. Remember, wires are flexible things. They're not only flexible in reality, they're flexible in your imagination. You can redraw things I like rectangles, and most students like that as well. So here's my capacitor right in there. But so now I've got 2 amps flowing through here, and this is a 1 ohm resistor, right? 1 ohm. So I'm starting off with 10 volts up here. I've got 1 amp going through, 2 amps going through this 1 ohm resistor. So what's my voltage drop from here to here? So delta V equals IR equals 2 amps times 1 ohm for that 1 ohm resistor. Well, that's a voltage drop of 2 volts. So if I start off with 10 volts and then I drop by 2 volts, what's my voltage right here? It's 8 volts. So right in there, I'm at 8 volts. The electricity has 8 volts, 8 joules of energy per coulomb of charge moving through across this point. Now let's look on the other side through here. Delta V equals IR. Now over here, see, this is an 8 ohm resistor, right? And I've got 1 amp of current flowing through this branch. That's what I figured out before. 1 amp going through 8 ohms. So that's an 8 volt drop. Yes? Okay, so we started off at 10 volts. We dropped 8 volts. So what does that leave over here? 2 volts. So we get, so delta V across the capacitor is this. Well, I have 8 volts over here minus 2 volts over here, 6 volts. I've got a 6 volt drop from here to here. Now, by the way, where is the positive charge going to be? Well, I need to step down in voltage from here to here. When I step down in voltage, that means I have to go with an electric field. So I have to have an electric field that's pointing to the right here. So this is going to have positive charge here and negative charge here. It didn't really ask for that, but you might. So anyway, that's my answer for part A. Okay? Now, let's do part B. In part B, we've got this situation. We now know what the voltage is. It's 6 volts. But we're going to take the battery away. So really what happens here is we're going to basically get the same circuit, but take the battery, disconnect the battery. So what I'm going to do is I'm going to redraw the circuit. All right, so now here's my capacitor. So this is for part B. And I'm going to redraw it. And if I come up here, I'm going to go through a 1 ohm resistor and then an 8 ohm resistor. So here's my 1 ohm. And here's my 8 ohm. And then I'm going to go back down to the other side. Think about it. If the charges are over here and these are all positive charges, they're going to discharge now. And they're going to branch right here. And all the current that goes through the 1 ohm resistor also has to go through the 8 ohm resistor to get to the other side. Yes? Okay. But then some of them are going to go over here. They're going to go through the 4 ohm resistor and the 2 ohm resistor. Okay? And we know this is 1 microfarad, and its initial voltage was 6 volts. So this is kind of what I'm given. Well, look. If the same current flows through the 1 ohm and the 8 ohm, then these two are in series. And then the 4 and the 2 ohm are in series. So basically, what I've got is, let's draw the capacitor out here. Let's move these wires around a little bit. It's as if, whoops, 1 plus 8 is 9. So I got a 9 ohm resistor. But look, the voltage drop from here to here is the same. So it's 6 volts. Thank you. So 4 plus 2 is 6 ohms. Oops, 6 ohms. So now this equivalent resistance and this equivalent resistance are in parallel. So what I can do now is figure out what the equivalent resistance is for these two in parallel. So the equivalent resistance is equal to 1 over 1/9 of an ohm plus 1/6 of an ohm. Okay, now somebody do the arithmetic for me. What was that equivalent resistance? 3.6? 3.6 ohms. So now look what we've got. We've got a discharging capacitor. We've got an equivalent resistance for the whole circuit, and we know what this guy is. Now, I want to show you something very cool that you can use to figure out RC circuits. If you can think graphically for a second. I'm going to draw, just by common sense, I'm going to draw what the graph should look like for voltage as a function of time on the capacitor. So here's time, and here's voltage. What's my initial voltage on the capacitor? 6 volts. Now as it discharges, what is the voltage going to be on the capacitor eventually? It's going to be 0, right? It's going to push all its charge out, and all that charge is going to go through these resistors, and all that energy that was stored in that capacitor is going to be dissipated into the environment by the resistors. So eventually there's going to be no more charge, no more energy stored in the circuit. So it's going to go down like this. Now, this is an exponential function. Well, think about this. The voltage is a function of time. It's going to be equal to the initial voltage, which we know is 6 volts, times e to the negative t over RC. Now, you always look at this guy, and you make sure that this matches this. Your other choice is going to be, maybe V initial equals, V is a function of time. Here's your other choice. So the voltage as a function of time is equal to the initial voltage times 1 minus e to the negative t over RC. Maybe it's that one. It's either going to be this or this when you're dealing with these functions. Which one matches the graph that we know is true just intuitively? Well, at time t equals 0, what should my initial voltage be? It should be 6. What is e to the 0 power? 1. V equals V initial. Yes, it's this one. Hooray. It's not this one, because this is going to be 1 minus e to the 0 is 1. 0, so the initial volt, so that would be for a situation that would be, curling up like this. All right? So whenever you have an exponential function that starts and then decreases down like this, you know this is the form of your equation you're going to use. And so now I can solve. I'm going to do this. I'm going to say V over V initial equals e to the negative t over RC. But what is V over V initial? What does it tell me in the problem? Well, it says it's going to drop to 1/10 of its initial voltage. So V over V initial is 1/10, or 0.1. So this is going to be 0.1. V over V initial is 0.1 times e to the negative t over RC. But we know what R is, right? It's that 3.6 ohms. We know what the capacitance is. It's 1 microfarad. We can solve for T. How do I solve for T? Take the natural log of both sides. The natural log of 0.1. Ooh, that's going to give me a negative value, which is going to cancel the negative that I get. Negative T over RC. And so T is going to be equal to negative RC times the natural log of 0.1. Now I just need to plug in my values. We said negative, and what was R again? 3.6 ohms. And then this was 1, was it 1? Yeah, 1 times 10 to the negative 6 farads times the natural log of 0.1. Plug all that into your calculator, and what do you get? 8.29 times what? 10 to the negative 6? Is that right? Or microseconds. And notice that this is negative, so it'll cancel that negative. All is well. We're not going back in time. That's not a lot of time, is it? That's a pretty quick little discharge we're going to get. But that's how you do it. There is a problem on the exam that requires you to take a ratio, like either your voltage or charge, like this, and solve for how much time it takes. So this is a really good problem to study. Okay? So, any final questions?